Hi, I'm Leela Huang, and today I'll present octsqueeze, an Octree structured entropy model for LiDAR compression. LiDAR sensors are an integral part of many robotics applications today. However, these sensors produce a significant amount of data. For example, the LiDAR sensor on a self-driving car can produce over 1 terabyte of data in one day. It is thus necessary to develop efficient compression methods for 3D LiDAR point clouds. Key challenges for compression are the sparsity of the points and the non-uniform density. As shown in this picture, areas close to the car are denser than the edges, which are very sparse. Prior work in point cloud compression includes tree-based methods, voxel convolution methods, and methods which compress image projections. Tree-based methods adapt best to sparsity while keeping 3D structure in mind, so we propose to enhance tree-based point cloud compression using a deep entropy model. Our method is built around the memory-efficient Octree data structure, which is a tree data structure created by recursively partitioning the space into equal octants and storing occupancy. Such a representation is advantageous because we stop dividing a node once it only contains one point, so it self-adapts to the non-uniform sparsity of LiDAR point clouds. We first quantize the point cloud by recursively partitioning it to create the octree, up to some depth. Since each internal node has exactly 8 children, its occupancy can be represented as an 8-bit symbol, and the tree can be efficiently serialized into a byte stream using breadth-first search. As we serialize the octree, we can collect contextual information about each node. All of this information is available during decoding. Next, we perform entropy coding to further compress this byte stream. The key intuition behind entropy coding is to encode high probability symbols into short codes after estimating a distribution for each symbol. If our estimates are close to the true distributions, we can achieve lower bit rates. Thus, we designed a tree-structured entropy model that exploits the hierarchical structure of an octree to better estimate the probability of a symbol appearing at each node. Our model consists of multiple MLPs stacked to aggregate ancestor information. The first MLP takes as input the context information for each node, while successive ones concatenate the output of the previous layer with parent output to take ancestral features into account. Each additional MLP allows us to aggregate information from one more level up the tree. Finally, encoding the byte stream using this entropy model gives us our final compressed bit stream. We evaluated our method on 2 challenging LiDAR datasets, a new dataset of urban and highway environments in North America, and the public self-driving dataset Kitty. We quantitatively measure reconstruction quality using point-to-plane PSNR, a common metric for point cloud similarity which uses distances to planar approximations of the point cloud, as well as voxel occupancy IOU. Holding reconstruction quality equal, our approach reduces bit rates by 10 to 20% compared to previous state-of-the-art methods. Next, we show qualitative comparisons of our method to the ground truth uncompressed point cloud and baselines. At similar bit rates, our method has lower error in all areas of the point cloud. From this side-by-side comparison, we see that point clouds compressed using our method retain high perceptual similarity to the original point clouds, while requiring much fewer bits of storage. Moreover, we can control compression rates by simply tuning the maximum depth of the octree. A smaller depth yields lower bit rates at the cost of greater distortion. Another important metric for compression is the effect on the performance of downstream tasks. Here we show mean IOU for semantic segmentation. At similar bit rates, our method outperforms all baselines. Comparing results for semantic segmentation on uncompressed point clouds and point clouds compressed using our method, the results are nearly identical. We also perform an analogous experiment for object detection. Again, we observe that our compression algorithm has minimal impact on the performance of object detection models. In summary, we presented octsqueeze, a deep tree-structured entropy model on an octree representation of the points. Our approach significantly reduces the bit rate and achieves a lower error on downstream tasks compared to prior work. Thank you for listening.